Imagine a grain of sand representing our entire home galaxy. To represent every galaxy in the observable universe, you would need enough sand to fill several Olympic-sized swimming pools. If the Milky Way is such a massive giant among its peers, why does it become almost invisible when we zoom out? What if everything you thought you knew about the size of the cosmos was only the beginning tonight? We take a journey that will change how you perceive everything. We are going to explore the true scale of our home, the Milky Way, and discover where it truly sits in the cosmic order. For most of human history, we looked at that band of light stretching across the night sky and had no idea what it really was. We now know that our galaxy is not just big, it is enormous. The Milky Way stretches about 100,000 light-years from one side to the other. To put that in perspective, light travels at about 186,000 miles per second, yet it still takes 100,000 years to cross our galaxy. Within this vast spiral structure, there are somewhere between 100 billion and 400 billion stars. Our own sun is just one of these stars, tucked away 26,000 light-years from the galactic center in a quiet neighborhood called the Orion Spur. Here is the truth that most people do not realize: the vast majority of galaxies in the universe are actually tiny compared to ours. Most are dwarf galaxies, with only a few billion stars. In fact, about 95% of all galaxies in the universe are smaller than the Milky Way. We are not average. We are in the top 5% by size. We live in a cosmic giant. Yet even this giant starts to shrink when we look at the structures that lie beyond. This is the paradox of our existence, being both enormous and tiny at the same time. The Milky Way is far from alone in the darkness. We belong to a cosmic family of about 50 galaxies, known as the Local Group. Within this neighborhood, which stretches 10 million light-years across, the Milky Way and Andromeda are the two undisputed giants. Andromeda, our closest large neighbor, sits 2.5 million light-years away. It is a monster compared to us, containing 1 trillion stars, more than double our own stellar count. Gravity is slowly pulling our two galaxies together, leading to a massive merger in 4.5 billion years. However, space is so empty that individual stars will almost never collide. Instead, we will eventually dance together to form a single, massive elliptical galaxy. Hovering near us are smaller companions like the large and small Magellanic Clouds. Though they look like simple, fuzzy patches in the night sky, they are actually separate galaxies with billions of stars of their own. These, along with dozens of other dwarf galaxies, orbit the Milky Way and Andromeda, like small children following their older siblings. While this collection of 50 galaxies seems vast, it is merely one tiny island in a much larger sea. We are about to see that our entire neighborhood is just a speck in the Virgo Supercluster, a structure so massive it begins to defy human comprehension. Shutterstock. As we pull further away, our perspective shifts from individual galaxies to massive structures known as superclusters. The Local Group is merely one small piece of the Virgo Supercluster, a titanic collection of galaxy clusters bound together by gravity. This is exactly what it sounds like: a cluster of clusters, containing at least 100 distinct galaxy groups. At its heart lies the massive Virgo cluster, located 54 million light-years away and housing as many as 2,000 galaxies. Many of these galaxies are absolute monsters, far larger and more dominant than our own Milky Way. The scale here is truly staggering. The Virgo Supercluster spans approximately 110 million light-years and contains about 100 trillion stars. To help your mind grasp this, remember that the Milky Way seemed huge at 100,000 light-years wide, yet the Virgo Supercluster is 1,100 times wider than our entire galaxy. If this supercluster were the size of a bustling city, the Milky Way would be smaller than a single house. In fact, it would be no more than a single room within that house. We are starting to see that even a cosmic giant like the Milky Way is just a tiny, fragile speck in the face of such overwhelming grandeur. Just when we thought the Virgo Supercluster was the ultimate boundary, astronomers in 2014 discovered that we are part of something even more incomprehensible. They found that our entire supercluster is merely a small branch of a much more massive structure called Laniakea. The name comes from the Hawaiian language and means immeasurable heaven, a fitting title for a structure so vast that it challenges the limits of human imagination. Laniakea is a supercluster of superclusters, home to 100,000 galaxies stretching across 520 million light-years. In this immense web of light, the Milky Way is not a fixed point. We are falling along with everything else in Laniakea toward a mysterious region of high mass known as the Great Attractor. To understand the sheer scale of this, imagine shrinking Laniakea until it could fit inside a large room. In that comparison, the entire Milky Way would be no larger than a single grain of sand. We have journeyed from thinking our galaxy was the entire universe to realizing it is less than a speck of dust in a structure so large it defies easy comprehension. However, as massive as Laniakea is, it is still only one supercluster among many in a universe filled with even larger cosmic filaments. When we map the distribution of galaxies across the deepest reaches of space, we see that they are not scattered at random. Instead, they cling to massive filaments of light, forming a structure that looks like a tangled cosmic web. These threads of galaxies stretch across billions of light-years, connected by gravity and separated by terrifyingly vast, empty regions called voids. Voids make up about 80% of the universe's total volume. One of the largest is the KBC void, an empty expanse roughly 2 billion light-years across. If you were placed in the absolute center of this void, the nearest galaxy clusters would be 1 billion light-years away so far that even the brightest stars would appear as nothing more than a faint, indistinguishable smudge. Our entire galaxy could fit across the width of this single void 20,000 times over. Within this web, the observable universe, the part we can actually see, stretches 93 billion light-years from end to end. This number is staggering because the universe is only 13.8 billion years old. The reason we can see so far is that space itself has been stretching, carrying distant galaxies away even as their light travels toward us. In this vast arena, astronomers estimate there are 2 trillion galaxies. If every galaxy were a single grain of sand, we would need enough sand to fill several Olympic-sized swimming pools just to represent them all. In that massive collection, the Milky Way would be just one grain, indistinguishable from trillions of others. However, not all grains of sand are created equal. To truly grasp the scale of a galactic monster, we must look at IC1101. This is one of the largest galaxies ever discovered, and it is a true king of the cosmos. While the Milky Way stretches 100,000 light-years, IC1101 is 6 million light-years across. That makes it 60 times wider than our entire home. If the Milky Way were the size of a single penny, IC1101 would be the size of a large pizza. This supergiant elliptical galaxy contains approximately 100 trillion stars, 250 times more than the Milky Way. It is so massive that if it were placed where our galaxy sits today, it would swallow our nearest neighbors, including the Andromeda galaxy, which is 2.5 million light-years away. IC1101 sits at the center of the Abell 2029 galaxy cluster, over 1 billion light-years from Earth. Its mass is estimated at 100 trillion times the mass of our Sun. If you lived on a planet within IC1101, your night sky would be unlike anything we can imagine. The density of stars near the center is thousands of times higher than what we see from Earth. Stars would shine in every direction, some as bright as Venus or Jupiter, creating a nearly continuous golden glow across the heavens. Traditional constellations would be impossible to see because the light of 100 trillion suns would wash away the darkness. IC1101 became this monster by being a cosmic cannibal. Over billions of years, its immense gravity has ripped stars away from smaller neighbors, consuming dozens or even hundreds of galaxies to fuel its growth. It is the result of a violent history, sitting at the heart of a cluster where it continues to grow fat by eating its neighbors. But what holds this entire web together? It is not just the stars we can see. The true scaffolding of the universe is dark matter. It forms the invisible tree upon which the galaxies hang, like lights on a Christmas tree. Dark matter provides the extra gravity that prevents the Milky Way from flying apart and allows giants like IC1101 to reach their impossible proportions. We are part of a structure held together by forces we cannot see, stretching across a web that is incomprehensibly vast. Compared to these absolute monsters and the infinite threads of the cosmic web, the Milky Way might seem small, but remember, we are still exceptional. We are still a giant among the trillions of dwarfs that fill the voids. We exist in that perfect, quiet balance between the tiny and the titanic. In 2003, astronomers analyzing data from the Sloan Digital Sky Survey stumbled upon a structure so massive it redefined our understanding of cosmic scale. They called it the Sloan Great Wall. This is not a single object, but a colossal sheet of galaxies, stretching approximately 1.37 billion light-years across, located about 1 billion light-years from our home. It contains tens of thousands of galaxies, all gravitationally bound in a cosmic membrane. To help your mind grasp this scale, imagine for a moment that the Milky Way is the size of a single grain of rice. In this comparison, the Sloan Great Wall would not just be the length of a football field, it would be longer than 10 football fields placed end to end. This structure was hidden from us for centuries, because we could only see the galaxies as flat points on the sky. It was only when we mapped their three-dimensional positions that this coherent, billion light-year long wall emerged from the darkness. But the Sloan Great Wall is not the only titan in our sky. Even earlier, in 1989, researchers discovered the CFA-2 Great Wall. While it is smaller than the Sloan Wall, it is still an enormous filament stretching 500 million light-years long and 200 million light-years wide. What makes this structure particularly special is our connection to it. The Virgo Supercluster, which houses the Milky Way, is actually part of this wall. We are quite literally living on one of these cosmic membranes, a tiny speck among tens of thousands of others that make up the wall. These structures are the result of a process that began shortly after the Big Bang. In the early universe, tiny fluctuations in density allowed gravity to pull matter together. Over billions of years, denser regions attracted more matter, while less dense regions became the vast empty voids we see today. The result is a cosmic web where galaxies cluster along filaments and walls, surrounding pockets of nothingness that are hundreds of millions of light-years across. However, even the Sloan Great Wall is small compared to the ultimate champion of size, the Hercules-Corona Borealis Great Wall, discovered through the mapping of gamma-ray bursts. This is the largest known structure in the entire observable universe. It is a galactic filament so vast that it stretches across 10 billion light-years. Consider that number for a moment. Our Milky Way is 100,000 light-years wide. The Hercules-Corona Borealis Great Wall is 100,000 times larger than our entire galaxy. If you were to travel at the speed of light, it would take you 100,000 years to cross the Milky Way. To cross this Great Wall, it would take you 10 billion years. That is more than 70% of the total age of the universe itself. The existence of a structure this large has created a profound crisis in the world of physics. According to our standard models of how the universe evolved, there simply should not have been enough time for something 10 billion light-years wide to form. Gravity is a slow force. Computer simulations of the cosmos predict that the largest structures should be no more than 1.2 billion light-years across. The Hercules-Corona Borealis Great Wall is roughly 10 times larger than what our best theories say is possible. Its presence suggests that the universe is far stranger and more complex than we ever imagined, or that our understanding of gravity and time is still incomplete. When we stand in the shadow of such a structure, the Milky Way becomes utterly insignificant. You could copy our entire galaxy 10 billion times and string them end to end, and they would only just match the length of this one cosmic filament. We are part of a vast, dark matter scaffolding that holds everything together. The galaxies we see are merely the visible lights on a massive, invisible tree of dark matter. We sit on one of these filaments, held by forces we are only beginning to understand. Part of a web that is incomprehensibly vast. This is the true scale of our home. We are small, yet we are part of a structure that spans the breadth of time and space. We are a single point of light in a wall that stretches across the very horizon of the universe. In the first moments after the Big Bang, the universe was almost perfectly uniform. Imagine a thick, hot soup of matter spread evenly throughout space, with only the tiniest variations in density. These variations, known as quantum fluctuations, were incredibly small. We are talking about differences of maybe 1 part in 100,000. However, in a universe governed by gravity, those tiny differences were everything. In regions that were slightly denser than average, gravity began to pull in more matter, a process astronomers call gravitational collapse. This was a runaway process. As more matter accumulated, the gravitational pull grew stronger, attracting even more material from the surroundings. Within the first few 100 million years, the universe began forming what we now call mini-halos, clumps of dark matter, each containing about 1 million times the mass of our Sun. These halos acted as cosmic cradles. Hydrogen and helium gas fell into these dark matter traps, cooling and condensing until the very first stars ignited in the darkness. These first stars were vastly different from the stars we see tonight. They were made of pure hydrogen and helium, with absolutely no heavy elements like carbon or iron. They were also massive, often 100 or more times the mass of our Sun. Because of their size, these giants lived fast and died young, exploding as magnificent supernovae after only a few million years. Yet, their deaths were a gift to the future. These explosions enriched the surrounding gas with the first heavy elements, allowing the next generation of stars to form with more complex chemistry. This chemical enrichment was the essential first step toward the formation of rocky planets and, eventually, life itself. As time marched on, these mini-halos did not stay isolated. Gravity drew them toward one another in a violent and beautiful dance of mergers. Two mini-halos would fall together, their dark matter combining and their stars mixing to form larger and larger structures. By approximately 1 billion years after the Big Bang, the first true galaxies had formed. These early galaxies were small by our current standards, perhaps containing only a few billion stars, but they were hungry. They grew by consuming gas from the space between them and by merging with other small neighbors. The Milky Way was born from this very process. It was not created all at once in a single moment of grandeur. Instead, it grew gradually over 13 billion years through a relentless series of mergers and accretion. We can still see the evidence of this ancient history today. The oldest stars in our galaxy, found in the halo and in tight clusters called globular clusters, formed more than 13 billion years ago within those first small primitive galaxies. When those small galaxies merged, they deposited their stars into what would eventually become the Milky Way. Astronomers today practice a field called galactic archaeology to piece this history together. By analyzing the chemical signatures of stars, they can identify groups of suns that formed together in the same ancient, long-vanished galaxy before it was swallowed by our own. We have identified several of these ancient dwarf galaxies that gave their lives to build ours. In a very real sense, and the Milky Way is not a single entity, but a composite, a collection of many smaller galaxies that merged over eons. This process of growth has never truly stopped. Even now, a small structure called the Sagittarius dwarf elliptical galaxy is in the middle of merging with the Milky Way. Over the next few billion years, it will be completely absorbed, and its stars will become part of our galactic halo, the large and small Magellanic Clouds. Those beautiful patches of light in the southern sky are destined for the same fate. This is the way of the universe. The large consume the small to reach sizes that are truly staggering. The final size of a galaxy is determined primarily by the mass of its dark matter halo. A larger halo can hold more gas and stars, allowing for a more massive galaxy. Our own dark matter halo is estimated to contain about 1 trillion times the mass of our Sun. While that sounds massive, it pales in comparison to giants like IC1101, which has a halo 60 to 100 times more massive. However, the era of rapid growth is coming to an end. As the universe expands and galaxies move further apart, mergers are becoming less common. Today, the Milky Way is essentially a middle-aged galaxy that has reached a stable size. It will remain roughly this way for another 4.5 billion years, until our final major merger with Andromeda changes everything once again. We are the survivors of a 13 billion-year cosmic lottery, built from the remnants of countless smaller worlds that came before us. The Milky Way is currently on a collision course with the Andromeda galaxy, our massive neighbor located approximately 2.5 million light-years away. Andromeda is a true titan of the local group, containing about 1 trillion stars, which is more than double the population of our own galaxy. While 2.5 million light-years sounds like an unreachable distance, gravity is pulling us together at an incredible speed. In about 4.5 billion years, these two giants will finally meet. It is important to understand that this event will not be a violent crash in the way we imagine a car accident. Instead, astronomers describe it as a majestic, multi-billion-year merger. Despite there being hundreds of billions of stars in each galaxy, the distances between individual stars are so vast that actual collisions between them are incredibly unlikely. They will simply pass by one another like ghosts in the night. However, the gravitational pull between the two galaxies will be intense enough to completely disrupt their beautiful spiral structures. Computer simulations show a spectacular cosmic dance. The two galaxies will approach, pass through each other, and then fall back together again. They will repeat this dance several times over several billion years, each pass stripping away gas and stars. Eventually, the two will settle into a single, enormous structure that some astronomers have nicknamed Milkomeda, or Milkdromeda. By the time this process is complete, roughly 6 billion years from now, the result will be a giant elliptical galaxy containing approximately 1.5 trillion stars. This new galaxy, Milkomeda, will be a retired world. Most elliptical galaxies of this size have used up their gas and stopped forming new stars. While it will be the dominant force in our local neighborhood, it will still be nothing special on a cosmic scale, remaining far smaller than monsters like IC1101. Over tens of billions of years, the rest of the local group will also collapse into this single structure, as Milkomeda consumes the smaller dwarf galaxies that surround it. But as Milkomeda grows, the universe around it will begin to change in a terrifying way. We live in an expanding universe, and that expansion is not just constant, it is accelerating. Distant galaxies are moving away from us faster and faster every day. Eventually, billions of years from now, they will be moving so fast that their light will never be able to reach us again. The observable universe will effectively shrink. Imagine the astronomers of the far future living inside Milkomeda. When they look out into the night sky with their most powerful telescopes, they will see absolutely nothing beyond the stars of their own galaxy. All other 2 trillion galaxies that we see today will have been carried away by the expansion of space, pushed forever beyond the observable horizon. These future beings will be completely isolated, trapped in a single island of light surrounded by an infinite empty darkness. They may even return to the ancient belief that their galaxy is the entire universe, simply because they will have no way to prove that anything else ever existed. Everything beyond their reach will be gone forever. This is the dual nature of our future, a grand merger that creates a trillion-star empire, followed by a slow descent into total cosmic solitude. It reminds us that our ability to see the 2 trillion galaxies of the cosmic web is a privilege of our specific time in history. We are living in a golden age of astronomy, where the universe is still close enough for us to see its true magnificent scale before the darkness carries it away. The first rung of this ladder, used for stars within our own Milky Way, is called parallax. It relies on basic geometry and the motion of the Earth. As our planet orbits the Sun, nearby stars appear to shift slightly against the backdrop of much more distant, stationary stars. You can experience this yourself with a simple experiment. Hold your finger out at arm's length and look at it with only your left eye. Then switch to your right. Your finger appears to move against the wall behind it by measuring that tiny angle of shift for a star. Astronomers can calculate its distance with incredible precision. However, parallax only works for our closest neighbors within a few thousand light years. To go deeper, we need a different kind of light. This brings us to the second rung, standard candles. These are celestial objects with a known intrinsic brightness. If you know exactly how bright a light bulb is, you can tell how far away it is just by seeing how dim it looks from where you are standing. The most famous of these are Cepheid variable stars. These stars pulsate, growing brighter and dimmer over a regular period. Astronomers discovered that the time it takes for a Cepheid to complete one pulse is directly related to its true luminosity. By measuring the pulse, we know how bright the star truly is, and by comparing that to how faint it appears in our telescopes, we can calculate the distance to the galaxy that holds it. The Hubble Space Telescope revolutionized our understanding of the universe by observing these Cepheid variables in galaxies tens of millions of light years away. It allowed us to see that the universe was far larger and expanding far faster than we had ever dreamed. But even Cepheids eventually fade from view as we look deeper into the cosmos. To reach across billions of light years, we must look for the most violent events in the universe type Ia supernovae. These are exploding stars that all reach roughly the same peak brightness, making them the ultimate standard candles. They are so incredibly bright that they can be seen from the other side of the observable universe. These cosmic markers allowed us to discover that the expansion of the universe is not slowing down, but accelerating, driven by the mysterious force we call dark energy. Yet, as we reach the furthest rungs of the ladder, we must acknowledge a humbling truth. Every measurement has an uncertainty. When we say the Andromeda galaxy is 2.5 million light-years away, that number carries an uncertainty of about 100,000 light-years. As we look further out, to the edge of the observable universe at 93 billion light-years, we are no longer measuring distances directly. Instead, we are inferring them based on mathematical models of how space has stretched since the Big Bang. Today, the James Webb Space Telescope is pushing these boundaries even further. It is observing galaxies that existed when the universe was less than 1 billion years old, helping us refine our measurements and rewrite the history of our cosmic home. This ladder is not just a tool for measurement, it is our only way to comprehend the staggering scale of the Milky Way and the 2 trillion galaxies that surround it. It shows us that while we are small, our capacity to understand the vastness of space is truly limitless. The normal matter that makes up everything we know, the atoms that build our lives and our galaxy, accounts for only about 5% of the universe's total energy content. The rest is made of 2 mysterious components, dark matter and dark energy. While we cannot see them with our eyes or our most advanced telescopes, their influence over the Milky Way is absolute. Dark matter makes up about 27% of the universe. We know it is there because we can measure its gravitational effects. For decades, astronomers noticed that galaxies, including the Milky Way, rotate in ways that simply do not make sense if we only count the visible stars. If the stars were the only things providing gravity, our galaxy would fly apart. The stars in the outer edges are moving so fast that they should be flung into deep space. Yet they remain held in place by an invisible hand. This hand is the dark matter halo. The Milky Way is surrounded by a massive sphere of this invisible material that extends far beyond its visible stars. This halo contains about 10 times as much mass as all the visible matter in our entire galaxy. Without it, the Milky Way could not exist. Think of dark matter as the scaffolding or the underlying structure of the universe. The galaxies are just the visible parts, like lights on a Christmas tree, while dark matter is the tree itself that holds everything together. Even the monster galaxy IC 1101 is surrounded by a dark matter halo that is proportionally larger, containing far more mass than our own. But as mysterious as dark matter is, dark energy is even stranger. It makes up about 68% of the universe's energy content, and humanity has almost no idea what it actually is. We only know it exists because the universe's expansion is not slowing down, it is accelerating. Something is actively pushing space apart. Dark energy is the ultimate force of isolation. While gravity tries to pull things together, dark energy pushes them away. In our current era, the Milky Way is still part of the grand cosmic web, but billions of years from now, dark energy will likely tear apart even gravitationally bound structures like galaxy clusters. Eventually, it might even overcome the gravity holding the Milky Way together, potentially ripping our galaxy apart, star by star. This means that while the Milky Way seems small compared to the vast structures of the universe today, it might appear relatively larger in the distant future, as dark energy pushes the superclusters and filaments apart, making the universe less dense. Galaxies will become lonely islands in a vast, empty sea. In that far-off time, our merged form with Andromeda might be one of the only remaining structures we can see. Understanding these invisible forces changes how we perceive our giant galaxy. We are not just a collection of stars, we are a small pocket of light living within a massive cloud of dark matter, caught in a cosmic tug-of-war with dark energy. It is a reminder that the universe is far more complex than the light we see. Most of our home is hidden, and the forces that will decide our ultimate fate are things we are only just beginning to name. Our dually exceptional and tiny galaxy is a passenger on a journey through a dark, expanding ocean. We are 5% light, surrounded by 95% mystery, and yet, here we are, stardust that has learned to measure the darkness. When we consider that there are about 2 trillion galaxies in the observable universe, the numbers become absolutely staggering. Each of those galaxies contains anywhere from millions to trillions of stars. Astronomers estimate that there are approximately 200 billion trillion stars in the observable universe, that is A2, followed by 23 zeros. For a long time, we wondered if planets were rare, but the Kepler Space Telescope changed everything. It showed us that planets are common, not rare. In fact, most stars have at least one planet orbiting them, and many have several. If even a tiny fraction of these planets are capable of supporting life, the potential for neighbors is enormous. If just 1 in every million planets could support life, that would still result in 200 trillion potential homes for living things. And if intelligent life arises on just 1 in every million of those life-bearing worlds, there would still be 200 billion civilizations in the observable universe. Yet, as we look up at the night sky, we have never detected a single signal. We have never heard a voice from the void. The galaxy seems completely silent. This is known as the Fermi paradox, and it remains one of the deepest mysteries in science. Where is everybody? There are many theories to explain this profound silence. Perhaps life itself is much rarer than our mathematical models suggest. Maybe the jump from simple single-celled life to complex, multicellular life is a hurdle so difficult that few ever cross it. There is also the darker possibility that intelligent civilizations tend to destroy themselves through war or environmental collapse before they ever gain the technology to reach out to the stars. It is possible they are out there right now, but they are staying quiet to avoid detection, or they are communicating in ways that our current technology simply cannot perceive. However, there is a more humbling possibility that we must consider. It might not be that life is missing. It might simply be that space is too big. The distances between stars are so vast that even if civilizations are common, they may never encounter each other. Our own Milky Way is 100,000 light-years across. If a radio signal were sent from a civilization on the far side of the galaxy today, it would take 100,000 years to reach us. By the time we receive the message, the civilization that sent it might have been extinct for 90,000 years. If civilizations are spread across all 2 trillion galaxies, the isolation becomes even more extreme. Our nearest large neighbor, the Andromeda galaxy, is 2.5 million light-years away. A signal from there would take 2.5 million years to reach us. Most other galaxies are billions of light-years away. The universe is so unimaginably large that billions of civilizations could exist right now and still never make contact with one another. The scale of the universe is not just humbling, it is profoundly isolating. Even if we are not truly alone, the distances are so great that we are effectively alone. We are like shipwrecked survivors on an island in an endless ocean, seeing lights on the horizon but knowing we can never reach them. This perspective should change how we look at our own world. You are made of atoms that were forged in the hearts of stars that died billions of years ago. Those atoms drifted through the vacuum of space for eons before coming together to form the Earth and, eventually, you. You are a way for the universe to know itself. Out of all the countless planets and all the galaxies across all of space, you are here, able to think about these questions and feel the weight of this vastness. The Milky Way may be small compared to the total universe, but it is our only home. Every star you see, every constellation we have named, and every story we have told about the night sky belongs to this one spiral. In a universe that is mostly empty and silent, our existence is a miracle of stability and time. The true scale of the Milky Way is defined by a strange duality. When we compare it to most galaxies, the tiny dwarfs that make up 95% of the cosmos, the Milky Way is a titan. It is comfortably in the top 5% of all galaxies by size, an exceptional and massive superpower of the local universe. Yet, when we stand next to supergiant ellipticals like IC1101 or gaze at the 10 billion light-year span of the Hercules-Corona Borealis Great Wall, our mighty home becomes a mere speck of dust. It is like being a tall person in a crowd who suddenly stands next to a skyscraper. You are still tall, but your height feels irrelevant in a larger context. For most of human history, we believed we were the center of everything. We thought the stars revolved around us and that our world was the focus of the divine. Every discovery since then has knocked us down a peg. We learned the Earth orbits a star. that the star is one of billions in a galaxy, and that the galaxy is one of trillions in a web that may even be part of an infinite multiverse. This realization is profoundly humbling, but it is also liberating. We are not central or special in size, but our value comes from something far more rare. In all this vastness, Earth is the only place we know of where life exists and has become conscious. You are made of atoms forged in the hearts of dying stars billions of years ago. Those atoms drifted through the void until they came together to form you, a way for the universe to finally know itself. While the universe is mostly silent and empty, the Milky Way provided a stable, quiet corner that allowed consciousness to emerge over 4 billion years of calm evolution. The astronomer Carl Sagan famously described Earth as a pale blue dot caught in a sunbeam. Every human who ever lived, every war ever fought, and every dream ever dreamt unfolded on that one small world orbiting an ordinary star in a galaxy that is both a giant and a speck. This perspective does not make our lives meaningless. It makes them infinitely precious. We won the greatest lottery in history simply by being born here, protected by a magnetic shield and breathing air filtered by ancient forests. As we look to the future, the Milky Way remains our harbor. We may never be able to cross the 2.5 million light-years to Andromeda, or the billions of light-years to the distant walls of galaxies. We are confined to this spiral by the laws of physics, making the Milky Way the only home humanity will ever have. But that is enough. Our galaxy is vast enough to be exceptional and stable enough to be perfect. The next time you look up at that glowing band of light stretching across the sky, remember that you are looking at home. Every constellation and every myth humans have ever told belongs to this one extraordinary spiral. We are the survivors of 13 billion years of cosmic growth. Stardust that learned to care, to think, and to wonder. The universe is unimaginably large, and the Milky Way is just one island in that sea. But it is our island. The Milky Way is large, but the universe is larger. Holding both of these truths in your mind at once is what it means to truly understand our place in the cosmos. We are a small part of something much greater, and that connection makes our brief time under the stars all the more remarkable. Thank you for joining me on this journey. If you found value in this exploration, please consider liking this video and subscribing to the channel to help us continue these deep dives into the cosmos. Remember, no matter how vast the darkness, you have your place in the light. Good night, and sleep well under the stars.